So today I'm going to talk about exponent rules and kind of like how we have them or explain the rule that we use, because I feel like a lot of it is memorizing. Once you memorize a rule, you can apply it, and yeah, so I'm going to go behind some of the rules here. Maybe not all of them, but I will write all of them down. All right, so the first rule, or I guess the first thing that we should talk about, is when we have a number a, it's just some number. We just have a raised to the m power. This is the same thing as multiplying it over and over again, m times whatever number m is. An example of that is like 2 to the second power. That's 2 times 2. Imagine 2 to the 24th power. Then we have 2 times 2 times dot 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 times 2, 24 times. So that's the idea of an exponent. And then another thing that I want to make really clear is that there is very particular vocabulary here. So we have a base, and then we have the exponent up here. And we have to be clear about that because, and I'll give an example real quick. Let's say we have 2 to the third power. 2 is the base, and 3 is the exponent. And the reason why we have to consider this is because there will be times where the base is encased in these parentheses, and sometimes there will be a number on the outside or a negative on the outside, or maybe a negative on the inside. So let's give an example of some of these things before we dive into the rules. So first, let's consider 2x to the third power. This is not the same thing as 2x in parentheses to the third power, because this one we treat them very differently. So this is like a whole different guy over here. They're having a breakup, right? Let's put a little broken heart. The 2 is going to go separate, and the x's are going to go like this, right? Because this is the base and this is the exponent. So that's what happens. Now, when it's encased in these parentheses, it's telling you, I want this group to stay together the whole time while we're multiplying. So then what happens is we have 2x times 2x times 2x. I want you to look at this example. Let's say we have negative 2 squared, and we also have negative 2 in parentheses squared. These are not the same thing. So, like the previous example, this guy is going to go his own way, and these two numbers are going to have a little breakup. So the negative is going to go over there, and then let's perform our operation in a group, because this is our base. This is what we're raising to the power of. So then, when all is said and done, we get negative 4 in these parentheses. And what's that negative doing out there? Well, there's a lot of ways to think about this, but the way I do is I slap a 1 there because I can distribute, so then I get negative 4. And we're allowed to do this because we can multiply by 1 and leave the thing unchanged. So, let's do this one over here. Now this one is wrapped in a group. So like we did in the previous example over here, we got to keep it together. They're a family, right? So we do negative 2 times negative 2, because we're taking we're taking this family and we're raising it to that power. So a negative times a negative is a positive, and 2 times 2 is 4, so we get 4 as our final answer. So see, negative 4 is not the same as 4. So that's why we have to be really careful about what we're calling our base and how we operate with parentheses versus not parentheses. Alright, so now we can move forward. If I have a number to the m power times a number to the n power, this is the same thing as a number to the m plus n. Alright, let me show you why. So let's say I have 2 to the second power times 2 to the third power. Also, it's important to note that they have to have the same base. In this case, 2 and 2 are the same base, a and a are the same base. We'll always end up with the same base. Alright, so if I represent 2 to the second power, that's the same thing as 2 times 2 times 2 to the third power, which is 2 times 2 times 2. And then by associativity, this then becomes 2 times 2 times 2 times 2. I don't know if I said that 5 times, but I'm sure you get it. So then, does this look familiar? It does. It looks like 2 to the fifth power. It looks like just like any other exponent. So that is how we come across this conclusion. So this is our first rule. Practice it on this example. I believe this might be 81, but I am not 100% sure. Alright, I know it's going to be like 27 times 3. Yeah, okay, 81. Let's move on to the next exponent rule. So the next one is if we have an a to the m over an a to the n, this is the same thing as a to the m minus n. Alright, let's see an example of this. Let's do 2 to the 6th power over 2 to the 3rd. And if you remember canceling, we can cancel out these because they have something in common. So then we're left with 2 times 2 times 2 over 1, but we really don't need that 1 right now. So it's 2 times 2 times 2, and then we can rewrite that as 2 to the 3rd power. So that's where this rule comes from. Alright, our next rule is if we have a to the m times n. Oh, also, these have to be same base. That is very important. Okay, a to the m times m. Oh my god, a to the m to the nth power. I don't know if... Okay, there's like this song I'm thinking of, and it's like... Oh my gosh, it's by Fergie. Fergalicious, I think? Okay, anyway, I don't... Whatever. So this is not the same thing as a to the m plus n rule. They're very, very, very different. So this rule is very focused on what the base is. So we have a to the m n times, which looks like this. N times, however many times it is. 2 to the second power to the second power, or third power. So we have 2 squared times 2 squared times 2 squared. So this is 4 times 4 times 4. This is 16 times 4 is 64, which notice is the same thing as 2 to the 6th power. So the reason why it's not the same as this rule is because if we actually did have that rule, let's say 2, if we use that rule, then we get 2 to the 5th power, which is actually 32. So these are not the same thing. So that's why we have a very different rule. This one looks specifically at one base, which is this one right here. And this is what's happening that gets us to this rule. Oh, to this rule. All right. So the next rule that we have, which I probably should have started out with, is no matter what number we have to the 0 power is always going to give us 1. So here is another rule. If I have some number to a negative exponent, that's going to be the same thing as 1 over that number to that positive exponent. So we're keeping these numbers the same. The only thing that's changing is we're making it positive and we're also putting it underneath. Another thing that I want to mention is that these rules can go both ways. All right, so let's do an example of this rule. Let's say I have 2 to the negative 2. By applying my negative exponent rule, this is going to become 1 over 2 squared, and then 2 squared is 1 over 2 times, or 2 squared is 2 times 2, and then we end up with 1/4. So there is another one of our rules. Finally, the last rule that we have is rational exponents and radical form, I want to say. So if we have a to like a numerator over denominator, that is the same thing as a in the square root, where the denominator goes in this little part right here. By the way, in case you're curious, that little part is called index, or for now you can also say root, and then the base goes there. One final part though is that the n goes in the inside in the square root. So a very common example of this is, let's say we have 81 to the 1/2. By using our exponent rule, we're going to put the denominator on the outside. So we have 2 on the outside. We're going to have 81 on the inside. And then the 1, our numerator, is also going to go on the inside. And then if you remember the video about square roots, we ask, what number to the second power gives me 81? So I'm going to get rid of this 1 because we're only multiplying by itself one time. A square root is actually it just looks like this. It has a little 2 right here, but we can get rid of that because it's just a regular square root. Sometimes there are cases where you'll have a 3 or a 5, but then we can solve this. So the square root of 81 is 9. And oftentimes I hear people say that they're confused between rational exponents and like radical notation. So this is how I like to think of it. When I have a piece of a pie and I divide it up into 4 pieces, I give rations of that pie to people. So that is where the rational comes into play. And when we talk about radical, I like to think of this as some really weird geometric straight shape, and that there's a little surfer dude right here, and he's surfing, and his favorite word to say is rad. So this is radical. There is one final piece of information that I need to let you guys know, and that is you might use multiple rules at once. I apologize for this very messy handwriting. I have been writing homework with my hand all day, so my hand is exhausted. But yes, you might want to use, or you might use multiple rules at once. Also, recall to use PEMDAS. Because you might have cases where you have something like this. I don't know. Some crazy. And actually, I'm going to also say one more final thing. Let's say you have a problem that looks like this, and you don't know where to begin with the simplifying it, or it looks really complicated. Remember PEMDAS. You're going to start here. That's going to get you, by applying the exponent rule, x to the 30th y squared over x to the 4th y to the 1st. I know I don't need this one here, but we're going to leave it there, all right? Then we're going to apply another rule. We're going to look at these individually. So by applying my x to the m minus n rule, that's going to be x to the 30 minus 4, and then we have multiplication here. So we're going to apply that same rule to the y. So then we're going to have y to the 2 minus 1. By simplifying, we get x to the 26 times y to the 1. Fully simplified, we get x to the 26 times y. All right, that should leave you prepared to tackle simplifying exponents and switching them up, making them positive, going crazy, all right? As always, I'll leave some example problems, and yeah.